The main topic we're going to be looking at here is the idea of two molecules interacting with each other. If you just got, let's say, a molecule or an atom, some sort of very tiny particle, and another one, and they're interacting with each other. They could be attracting, they could be repelling, or maybe they cancel out and there's no forces at all. And that's ultimately going to depend on distance. How to calculate Lennard-Jones potential energy? Yeah, the whole idea of Lennard-Jones potential energy is it's the potential energy of these two particles interacting with each other. Specifically, two neutral particles. If they're charged, like if one of them is positive, the other one's negative, or if they're both positive or both negative, if they're charged, then the electric forces are so strong that it overwhelms everything else. So we would be focusing on just the electrical forces. But if they're neutrally charged, then the electrical forces are going to be pretty weak. And so we get some more subtle interaction between them. And just some terminology to start with. The distance we're talking about, because the amount of force and the amount of potential energy depends on the distance. So the terminology we're going to use, we're specifically talking about the distance from center to center. So just the straight line distance measured from the center of one of them to the center of the other. We're going to call that distance r. Distance from center to center right now. And of course, that could change as time passes. If the particles are moving towards each other, r decreases. If they're moving away from each other, r increases. So r can change as time passes, so we're going to treat r as the independent variable. Everything else is going to be based on r. We could talk about force as a function of r. We could talk about potential energy as a function of r. But r just represents the distance between particles measured from center to center. Another one of the important quantities we're going to be looking at, another distance, is the diameter of the particle, like how far it is from edge to edge through the center. And that distance we're going to call sigma. The Greek letter sigma represents the atomic diameter. And we're basically going to be using that as a unit of measurement. Instead of measuring r in inches or centimeters or meters, because it's going to be a ridiculously small number of meters, instead we're going to measure r in units of sigma. So like 1 sigma, 2 sigma, 3 sigma. We're just going to measure the distance as something sigma. So you can essentially treat sigma as a unit of measurement for distance. And of course, there will be a conversion factor depending on what atom we're talking about. Any given type of atom is going to have a certain value of sigma in like something times 10 to the negative 21 meters, a very small distance. But for most practical purposes, we can treat sigma as the unit of measurement. Any questions on that so far? So let's take a look at some of the extreme cases. Let's say the particles are very close together. If the particles are so close together that they're almost overlapping, what would you expect them to do?
Or repelling each other?
Yeah, they're going to repel. Because you can't really push atoms, like if you're pushing atoms towards each other, you can't push them so close together that they're in the same space. Atoms can't occupy the exact same space. They're going to start repelling each other before they get there. And part of the reason for that is if you look at where the charge is actually located within an atom, I mean, we treat it as neutral, but neutral just means it has the same number of protons and electrons, same amount of positive and negative charge. But where is the positive charge located versus where is the negative charge located?
Positive is in the nucleus and negative is in the orbital.
Yeah, we've got positive charge packed close, tight, packed like really small into the center, and the negative charges spread out throughout the electron orbitals. So if you put these two atoms very close to each other, the electron shells start to sort of overlap, and those electrons are going to be repelling each other. So if the atoms get too close to each other, then they start repelling. So electrons if the atoms are very close, we get a repulsive force. And as far as direction is concerned, if the atoms are repelling each other, do you think we would want to call that force positive or negative if we had to assign a sign to it?
Negative.
And why is that?
They're moving farther apart from each other.
They are moving farther apart from each other, which means what's happening to the distance r?
It's increasing.
Right. So since r is increasing, we're actually going to call this a positive force. This is generally how we define positives and negatives. If we want to set up a coordinate system to describe force, usually we call a force positive if it's acting to increase some distance, and we call the force negative if it's acting to decrease some distance. So a repulsive force we're going to treat as positive. In other words, greater than 0. So that's what happens when the particles are very close. On the other hand, what's going to happen if the particles are kind of far away? In your experience, if you just have a clump of matter, does the matter just sort of drift apart, or does matter tend to stay close to stick together? It sticks together. Like this marker, for instance, is made of atoms. The atoms aren't drifting apart, repelling each other forever. They are sticking together. Even if I try to pull it apart, it resists that. The atoms are sticking together. They're attracting each other when I try to pull them apart. So, of course, if they're too close together, they're going to repel. But if they're a little bit further apart, they attract. They're trying to stick together. Matter tends to clump together, at least in solid form. So if the atoms are kind of far, further apart than too close, but not really far away, we get an attractive force. The atoms are pulling towards each other. And would we treat that as a positive or negative value?
Negative.
Yeah, that's going to be negative, again, based on what it does to R. An attractive force is trying to decrease the distance between the atoms, so we treat that as negative since it's trying to cause a negative change in R. And if very close means repulsive, but kind of far means attractive, what would you expect to happen at some specific distance between very close and very far? If you've got let's imagine graphing this. If you've got distance versus force, we know if the atoms are very close, if R is very small, the force is going to be positive. If the atoms are further away, the force is going to be negative. Yeah, there's going to have to be some sort of equilibrium. Force has to equal 0, right? If you've got a continuous function that's positive in one location and negative in another location, it can't just jump. If it's continuous, it's going to have to go through every point in between. And this probably isn't going to be a straight line, but regardless of what shape it is, it's going to have to pass through 0 somewhere. So there's going to be some R value that we can call equilibrium. Because you've got this complicated situation going on with the two atoms. You've got a mixture of several different forces. You've got this repulsive force, and you've also got an attractive force. They're both getting weaker as the particles get further away, but they get weaker at different rates. So when they're close, the repulsive force is stronger and dominates. When they're a little bit further, the attractive force is stronger and dominates. And then as they get really far away, both of the forces get weaker, and so the total force is going to get closer to 0. But there's going to have to be some location where it's the exact right distance such that the attractive and repulsive forces cancel each other out. That's what we call equilibrium, the distance, the location where the particles don't exert any forces at all. Or rather, they do exert forces, but the attractive and repulsive forces cancel out. And we typically call that location R0, or R sub 0. So R is a variable. R represents how far they are right now. R sub 0 is a specific value of that variable. It's the specific distance where they happen to cancel out the forces. And that distance ends up being a little bit further apart than touching. Because if the particles are exactly touching, you'd expect a repulsive force. They're too close together, so they're going to repel. If they're a little bit further apart, if this extra distance is exactly right, then we get the forces canceling out. So there's some distance between the particles where the forces cancel out and you get no force at all. That's equilibrium. If they're closer than that, they repel. If they're further than that, they attract. And this distance, if you take a look at the distances involved here, again, we're going to be measuring R from center to center. So this distance would be R. But what do we call the distance from center to edge? What would that distance be? It's a radius, right? It's just the radius from center to edge. And we're already calling the diameter sigma. So what would the radius be in terms of sigma? Right, that's half of sigma. This distance is half of sigma, sigma over 2. But then we've got another half sigma. If you add those together, you just get sigma. So if R, the distance between center and center, is exactly 1 sigma, that means the particles are just barely overlapping, just barely starting to overlap. So that would be, if R is exactly sigma, they're going to be repelling. The equilibrium distance is that plus a little bit of extra distance. So this distance, you've got half sigma plus half sigma plus a little bit extra. That little bit extra ends up being about 0.12 sigma, about an eighth of a diameter. And so this distance is 1 sigma, from the 1/2 sigma plus 1/2 sigma plus a little bit, ends up being about 1.12 sigma. So that's the standard we're going to be using. This is the general rule of thumb. The distance between particles that is equilibrium is about 1.12 sigma, or close to 1 1/8 sigma. So when R is about 1.12 sigma, that's the equilibrium distance, and we call that R sub 0. And of course, sigma is going to vary from atom to atom. Different atoms or different molecules are different sizes. But in general, the equilibrium distance is about 1.12 times the atomic diameter. Any questions on that so far? Yeah, force would be 0 at equilibrium. Equilibrium is specifically defined as this location where the forces cancel out. So the total force is 0 when the particles are equilibrium distance from each other. You could essentially treat that as the definition of equilibrium. Any other questions on that so far? So we can fill in a few more facts about the force. We can say at distance R naught, when R is R naught, which is about 1.12 sigma, the force is going to be 0. And then also what about, and we've covered when the atoms are very close, when the atoms are kind of far. What would you expect to happen if the atoms are very, very far apart?
No attraction.
Yeah, technically not no attraction. They are going to be attracting each other a little bit, but it's going to be very, very weak attraction. In general, any force that can act at a distance, like gravity or magnetism or electrical forces, Any force that can act at a distance is going to get weaker and weaker the further the objects are from each other. So as the objects get very far, the force is going to get very weak. It is still technically attractive, but very, very weak attraction. So if the atoms are very far, we get very weak attraction. The force is still negative, but it's going to be almost zero. Mathematically, we'd say the limit of the force is zero as r approaches infinity. Any questions on that so far? So we've got our list of facts about force. It seems like it should be a hashtag. You have subscribed to force facts. And so we can make a graph of force. Maybe make this a little more accurate. We know that at equilibrium distance, the force is going to be zero. If we're talking about distances closer than that, we're going to have a positive force. Distances further than that, we're going to have a negative force. Also, if the particles get really close, what would you expect to happen to the repulsive force? Could you actually push the atoms so close that their distance becomes zero?
No.
No, that's not possible. Because the closer you push them, the harder the pushback becomes, the stronger the repulsive force becomes. So we're actually going to get an asymptote here. The closer they get, the stronger the repulsive force becomes. So at equilibrium, the force would be zero. Beyond equilibrium, there's going to be a negative force. But that negative force becomes weaker and weaker, approaching zero, but never actually getting there. So our graph of force is going to look something like this, with an intercept at r naught, a minimum somewhere over here, probably an inflection point. So that would be a rough approximation of our graph of force between the particles. Any questions on that so far? The thing is, though, we don't really want a graph of force. What do we want to graph here? What has been, energy. And energy has been the main focus of this class so far. What we really care about is not just the forces that these particles exert on each other. We want to look at the energy that these particles have in relation to each other, specifically the potential energy. So what we're going to do is, in addition to this graph of force versus distance, we're going to use this as the framework to build another graph of potential energy versus distance. And to do that, let me mark equilibrium also, because equilibrium is going to be important on both of these graphs. To do this, we can use a very specific relationship between potential energy and force. How are those related? Do you have any equations that tie force and potential energy together? Yeah, force is the negative derivative of potential energy. Force is the negative derivative with respect to, I'm going to write this as derivative with respect to r, because we're talking about r as our variable here, our distance variable, derivative of potential energy. And this has to do with how we're defining potential energy. Potential energy is defined as the negative integral of force with respect to position. So if you know some sort of formula for force, or like in this case, we have a graph of force, if you had that function, you could integrate it and then apply a negative sign, and you get a formula for potential energy. Or alternatively, if you have a formula for potential energy, you could take the derivative with respect to distance, apply a negative sign, and that tells you the force. So this is how these are related. This is very closely tied to the idea of work that we've been looking at. Work being force times distance. You apply a force, as an object moves some distance, you're doing work. But work is just a transfer of energy. In this case, we'd be thinking of it as a transfer of potential energy, assuming you're just moving an object at a constant speed. So all you're doing is investing potential energy in it, no kinetic energy. That equals the force. But if you're applying a force, you're acting presumably against some other force. Let's say you're lifting an object, you're applying a force against gravity. Or if you're compressing a spring, you're applying a force this way, but the spring is pushing back the other way. So the force you're applying is the opposite of some existing force. The applied force is the opposite of the force we actually care about. And force times distance, that's fine if the force is constant. But if the force is changing, like when you're compressing a spring, you get a weak force, then a stronger force, stronger, stronger, stronger. So we'd have to add up a bunch of little tiny pieces. And what mathematical tool from calculus adds up lots of tiny bits? A derivative is more looking at the ratios of tiny bits, but what symbol adds up lots of tiny bits? The opposite of a derivative is, yeah, an integral. So the integral is really just adding up all these tiny bits. Integral of force with respect to distance is really just adding up all the little bits of work as the object moves. And the nice thing about the integral is it allows you to add up all the little bits even if the values are changing as you move. If the force wasn't changing, we would just take the force times the distance, and that's good enough. But if the force is changing, you can't just take one of the forces and multiply it by a distance. You've got to use an integral to add up all of the values of force times little bits of distance. That's really all an integral does. Did they ever tell you in calculus what this sign actually means, what it stands for? It's a summation. An integral is just adding up lots of little bits. And this is not just a clever mnemonic. This is where the sign comes from. The integral sign originated as a stylized S for summation. And literally all it's doing is adding up lots of little bits. If we write something like integral dx, integral means add up, dx means a tiny piece of x. Add up all the little bits of x and you get x. That's really all an integral is doing. It's adding up lots of little tiny bits. In this case, we're adding up lots of tiny bits of work to get the total transfer of energy. Any questions on that so far? So this is actually how we define potential energy. Potential energy is defined as the negative integral of force with respect to distance. Just a way to mathematically add up all the little bits of work. To reverse that, if you take the derivative of both sides, you get force is the negative derivative of potential energy with respect to distance, because derivative is the reverse of the integral. And this is a very useful formula as well, a very useful expression of how these quantities are related. First of all, it tells you how much force, the amount of force is exactly equal to how quickly the potential energy is changing as an object moves. So a strong force means lots of change in potential energy per meter. A weak force means only a little bit of potential energy per meter. No force means the potential energy doesn't change as you move from place to place. So the amount of force is all about how much the potential energy changes per unit of distance traveled. And this negative sign, how could we interpret that? What does a negative sign or a positive sign mean when we're talking about force? Like if we say that a force is positive or that a force is negative, what are we distinguishing there? Yeah, the negative or positive sign on force is all about the direction. So when we say opposite of derivative of potential energy, because you should interpret a negative sign like this as meaning the opposite of. This isn't saying the force is negative. This is saying the force is opposite of derivative of potential energy. In other words, opposite direction. You can interpret this as meaning the force is acting in a direction opposite to an increase in potential energy. Whichever direction the force is pointing should be the direction that potential energy is decreasing. Force points towards lower potential energy. For example, which direction is the force of gravity? Gravity is pulling, gravity pulls objects downwards. What happens to an object's potential energy as it moves in that direction? Is the potential energy increasing or decreasing or staying the same?
Decreasing.
Decreasing, yeah. So the gravity force is pulling in a direction that decreases the object's gravitational potential energy. You've got a high potential energy zone up here, a low potential energy zone down here. Gravity is pulling from the high potential energy zone towards the low potential energy zone. That is generally what forces do. If you have a force that's associated with a type of potential energy, that force is going to be pushing or pulling from the high potential energy zone towards the low potential energy zone, wherever that happens to be. This is also true for springs, for instance. If you have a spring that's stretched out, the spring force is going to be pulling towards equilibrium. If the spring is compressed, the spring is pushing outwards towards equilibrium, because equilibrium is the lowest potential energy. So the spring force is pushing or pulling towards that lowest potential energy zone, equilibrium. Any questions on that so far? So now that we've got this relationship between force and potential energy, let's see if we can draw out the graph of potential energy. In fact, what we can do, since we've got all these statements about force, all of these claims about force can be translated directly into claims about potential energy. For example, when the atoms are very close, the force is positive. If the force is positive, what does that tell you about the potential energy graph? If the force is positive, then what? What is the derivative really telling you about the graph? I wouldn't say the graph itself is negative, because this isn't saying the force is opposite of potential energy. It's saying the force is opposite of the derivative of potential energy. What does a derivative tell you about a graph? Yeah, it's the slope. So when the force is positive, that doesn't mean potential energy is negative. It means the slope of potential energy is negative. The force is the opposite of the slope of the potential energy graph. So we can translate all these statements about force into statements about the slope of the potential energy graph. If the force is positive, then the slope of the potential energy graph is going to be negative. So if the atoms are very close, the force is positive, so the potential energy slope is negative. In fact, let's go ahead and fill that in on the graph. In this region, we have to have a negative slope. If the atoms are kind of far apart, further than R naught, the force is negative. So that means the potential energy graph has to have a positive slope. So in this region, we have to have a positive slope. If the atoms are very far, the force is approximately 0. So the potential energy has approximately 0 slope. Potential energy slope is, let's say, almost flat, because the slope is getting closer and closer to 0. So further and further out, the slope gets flatter and flatter. Also, what do we know about the force at equilibrium, at R0?
It's 0.
Right, the force is 0, which means at that location, the potential energy has to have 0 slope. And think back to calculus. What happens to a graph if the function's slope is 0 at that instant, at that single location? If you set the derivative equal to 0, what are you looking for on that graph? Like, for instance, if you have a region where the slope is positive and then a region where the slope is negative, at the instant where the slope hits 0, what have you just found? Yeah, a turning point. Usually we describe that as a maximum or a minimum, or more generally a critical point. So a maximum if you've hit the high point and then gone back down, a minimum if you've hit a low point and then gone back up, more broadly a critical point. Or yeah, in physics we often call this a turning point because it's in the process of turning around or changing from increasing to decreasing or vice versa. So we're going to have a critical point here, either a maximum or a minimum. And we can tell which one by looking at the surroundings. In this region, we've got to have a negative slope. In this region, we've got to have a positive slope. It's got to hit flat at this instant. So it looks like that's a minimum because we've gone from decreasing potential energy, leveling off, and then to increasing potential energy. So broadly, we should expect a negative slope, flattening out, a positive slope, but also the slope should get flatter and flatter as we get further and further out. So we should expect the general shape to look something like this. Negative slope flattens out to a minimum at R0, and then becomes positive slope, but getting weaker and weaker slope, or flatter and flatter graph. So that general shape is what we're going to get. Any questions on that so far? And let's see if we can draw in a little more accuracy now that we've got the general basic shape. For the moment, I'm going to erase the axis because we don't want to make any claims yet about how much energy, how high or low above the axis this is. So getting rid of the r-axis for the moment. And just keeping the location of R0. We know we've got to have a minimum here. So I'm going to draw this kind of low. We know that at r equals R0, we're going to have a lowest possible value, a minimum, a turning point. It's got to be flat there. To the left, it's going to have a negative slope. To the right, it's going to have a positive slope. Also, what were we assuming happens to the force if you go closer and closer and closer and closer? If the atoms are getting closer and closer, what happens to the force? Yeah, the force increases. We get a very strong force. And a very strong force should correlate to a very steep slope. So as the atoms get closer, the potential energy graph is actually going to get steeper and steeper and steeper. And of course, it doesn't curve around because this is a function. It has to pass the vertical line test. But it's going to get steeper and steeper and actually ends up having the potential energy axis as a vertical asymptote. Meanwhile, to the right, we've got to have a positive slope. But since the force is getting closer to 0, the slope has to get closer and closer to 0. It has to flatten out. So negative slope if we're on the left side, of equilibrium if the atoms are too close. Positive slope corresponding to that attractive force if the atoms are further apart. But that force gets weaker and weaker, so the slope has to approach zero. We have to get flatter and flatter. In other words, this graph also has a horizontal asymptote. And in potential energy graphs, we generally have a choice of how high or low to put the distance axis, in this case, the r-axis. And if you have a choice of how high or low to put the axis, usually the most useful choices are either put the axis at the lowest point or put the axis at the asymptote. And the asymptote is usually much more important. So what we're going to do here, since we have the option of how high or low we want to draw the axis, essentially how we're setting up our coordinate system, we're going to use the asymptote itself as the r-axis. So this is what we call the Lennard-Jones potential energy graph. Lennard-Jones potential energy. Or for short, we often just abbreviate that as LJPE. And this represents the potential energy that a pair of particles have. If you've got a pair of subatomic, or not subatomic, a pair of atoms or molecules, a pair of very small particles that are neutrally charged and are reasonably close to each other and not interacting with anything else, this graph represents the potential energy they have by interaction with each other. So what you can do with this graph, there's a formula for it, of course, as well. This complicated looking equation with like a something over r to the 6th and a something over r to the 12th. I forget exactly what it is, but you can look that up and use it to get the exact values of energy at any r value. Or if you just need a good enough approximation, if you've got a fairly accurate copy of this graph and you want to know the energy at a certain location, you can just look up that distance on the r-axis, trace down to find the point on the graph, and look at the energy on the energy axis. So you can use this graph to interpret what's the value of energy at any location you want, any distance you want. So that's one of the main uses of this graph, being able to quickly predict what's the potential energy of this pair of molecules interacting with each other at a certain distance. Any questions on that graph so far? One other bit of terminology here. Generally, the most important part of a graph like this is the fact that it has an asymptote. But there's also a lowest value. This minimum possible potential energy is some specific amount of energy below the asymptote. And we call that difference in energy epsilon. So this difference in energy, the difference between the asymptote and the lowest point, is delta energy equals the Greek letter epsilon. So epsilon represents how different the asymptote and that minimum value are. If you're going epsilon below 0, what would be the actual listed value of this energy? If you're at 0 and you go down some amount we're calling epsilon, what's your new value?
Negative epsilon.
Right, so that's what we're going to call this energy value. Negative epsilon represents the energy of the minimum value, the lowest energy value. So negative epsilon is the lowest energy these particles can have. If the particles are exactly at equilibrium, their potential energy is negative epsilon. And of course, epsilon is going to be some specific amount of joules, usually a very small amount of joules, like something times 10 to the negative 22nd, 23rd joules, very small amount of energy, because these are just individual molecules or individual atoms. But epsilon is going to be a specific value for any type of atom. If you've got, let's say, 2 hydrogen atoms, there's going to be a certain value of epsilon for them. Or if it's 2 neon atoms, you're going to have a different value for epsilon. And also, you can mix and match. If you've got like 1 neon atom and 1 helium atom, there's going to be another epsilon value for that interaction. But the nice thing about using a variable instead of a specific amount of energy is that we can just use this one graph for any type of atom interacting with each other. You're going to have a minimum at location R0, energy negative epsilon. You can fill in the rest of the graph as this shape. And to get information about specific types of atoms, you just run your calculations in terms of R0 and epsilon, and then fill in those values as needed after you run the calculations. So we can work out a general theory for any type of atoms interacting with each other, and then fill in specific numbers as needed. Also, in the same way that we can list out distances as sigmas, like we could have 1 sigma, 2 sigma, 3 sigma, 4 sigma, and so on. The r-axis is usually going to be labeled in multiples of sigma. Likewise, the energy axis could be labeled as multiples or fractions or whatever of epsilon. Like, for instance, we'd probably mark this off as something like negative 1/4 epsilon, negative 1/2 epsilon, negative 3/4 epsilon, negative 1 epsilon. And then above the axis, we'd have positive 1/4 epsilon, positive 1/2 epsilon, and so on. So the energy axis is going to be marked off in epsilon as if that were a unit of measurement, because in a way, it is a unit of measurement. It's the unit we're using to measure energy at this atomic level. Any questions on that so far? And let's try one more thing we can do with this graph before we end for the day. If we take this potential energy graph, and let me try drawing a slightly more accurate rendition of it. So we're going to mark R0, negative epsilon. But presumably potential energy is not the only type of energy involved here. If these atoms, presumably they're not just staying still, they're going to be moving, which means what other type of energy do they have? Right, they're going to have kinetic energy. And if we have potential energy, and we also have the atoms having kinetic energy, and this is just going to mean the total kinetic energy of both atoms as they move, we can say potential energy plus kinetic energy is the total energy. In a closed system, what should we assume about total energy if these particles are only interacting with each other?
It's constant.
Right, total energy is constant. And on a graph, what would a constant look like?
A straight line.
Right. Specifically, I would say a horizontal line or a flat line. So let's say we know the total energy. Let's assume the total energy is, let's say, negative 1/2 epsilon. Let's say we know the total energy of these particles happens to be negative 1/2 epsilon. We could put E total all the way down at negative epsilon, but that would be the lowest possible energy, which just means the atoms aren't moving. They're just stuck at equilibrium. So to make things more interesting, let's say we put the total energy at negative 1/2 epsilon. We can just draw in a flat line representing that constant value. And this is, of course, just one example. You could set the total energy to any value you want, as long as it's negative epsilon or more. But let's say that E total happens to be negative 1/2 epsilon exactly. From that, from E total graph and potential energy graph, we should be able to find the kinetic energy values everywhere. And the most important one to look for, what's probably the most important single possible value of kinetic energy?
When it's 0?
Right, 0 is the extreme value. 0 is the lowest kinetic energy can be. If we want to know where is the kinetic energy 0, what has to be true about these in order for kinetic energy to be exactly 0? They have to be equal, right? You plug in 0 for kinetic energy, you just get potential energy equals E total. And we can find that directly on the graph. We've got a graph of potential energy, we've got a graph of total energy. Those are equal when what happens on the graph? Right, when they intersect. If we look for the intersections, those intersections tell us R values where kinetic energy is 0. In other words, the intersections of potential energy and E total tell us the R intercepts of the kinetic energy graph. And we typically call those R min and R max. Those represent the turnaround points. Those are where the particles get so close they have to come to a stop and then they bounce off each other. Or R max is when the particles get so far out they come to a stop and they bounce back in. And in between, what would you expect the kinetic energy graph to look like? Where would you expect kinetic energy to be highest?
At R naught.
Right, at R naught, potential energy is lowest, so kinetic energy is going to be highest. And specifically, if you solve this for kinetic energy, that's just E total minus potential energy. E total minus potential energy is the difference. This difference is 1/2 epsilon, so the value of kinetic energy is going to be 1/2 epsilon. And in between, potential energy decreases, comes to a minimum, and increases again. So kinetic energy has to do the reverse. Increase, come to a maximum, and then decrease again. So this would be our graph of kinetic energy. And that looks very similar to what other kinetic energy graph we've seen.
The spring mass system.
Exactly. This is almost the same, not exactly the same, but almost the same shape as what we get for the spring mass system. Since the kinetic energy graph of the two atoms looks almost exactly the same as the kinetic energy graph for the mass on a spring system, that means the behavior is going to be almost exactly the same. These objects are going to oscillate almost as if they were connected by a tiny invisible spring. So by looking at the kinetic energy graph, we can predict how these are going to move. We can figure out what their behavior is going to look like. Any questions on that so far?
The max for kinetic energy is at -1/2 epsilon or at negative epsilon? Like,
The maximum here would be, since it's above the axis, that would be positive 1/2 epsilon.
okay.
And that is literally just the difference between E total and potential energy. If you subtract negative 1/2 epsilon minus negative epsilon, you get positive 1/2 epsilon. So that difference tells you the value of kinetic energy at that location. In fact, that's true for any location. If you care about like this R value, you could take the difference between E total and potential energy. That difference is the value of kinetic energy at that location. So that's a very good visual way of sketching out the kinetic energy graph. At every location, look at the difference between E total and potential energy. That difference is the value of kinetic energy at that location. So if you want to get some more practice on this, what I would recommend is draw out some examples of this yourself. Draw the Lennard-Jones potential energy graph, or maybe you can find, if you can get a printout or a copy of this online. Get it as accurate as you can, a graph of the Lennard-Jones potential energy. Choose some E total, like just drawing a horizontal line at whatever level you want, and try drawing the kinetic energy graph based on that E total. Try that with several different E total values and see what changes as you increase or decrease the total energy. What does that do to the actual behavior of the particles? So give that a try. Try to develop an intuition for what happens to the behavior when you change E total. And I will see you next time.
Thank you.
You're welcome.